Okay, so excuse me, in this video, we're going to be talking about the polarity of molecules. All right. So as I explained before in my previous videos, that you can have a molecule with polar bonds, but it could be the molecule as a whole could be non-polar. All right. Now, if it is a non-polar molecule with non-polar bonds, of course, it'll be non-polar, all right? So H2Cl2, F2, methane, their bonds are non-polar to begin with. So the molecule as a whole is going to be non-polar. However, if you take the example of carbon dioxide, all right? Carbon dioxide has got two polar bonds. However, the shape is linear according to the VSEPR theory, all right? So carbon is 2.5 electronegativity value, oxygen is 3.5. That means there is an electronegativity difference of 1. All right, so you have one dipole in this direction, magnitude of 1, and then you have another dipole in pointing in the opposite direction, also a magnitude of 1. Remember, the arrowhead is towards the more electronegative atom, which in this case is oxygen, because it has a value of 3.5. Okay, so the magnitude of these dipoles are the same, 1, but in opposite directions, so they cancel. So even though the bonds in carbon dioxide are polar, the molecule is non-polar because the dipoles are canceling, all right? Now, when you apply this to CCl4, all right, or even CF4, which is symmetrical, you will see the same thing happening, all right? Carbon is about, I think it's 2.5, and chlorine is 3. So there is an electronegativity difference of 0.5, okay? So each dipole has a magnitude of 0.5. However, if you look at those dipoles, they are equal but opposite in direction. They're canceling each other out. All right. So the dipoles are canceling. Okay. So when you have symmetrical molecules with polar bonds, the dipoles cancel, and therefore symmetrical molecules with polar bonds are non-polar. All right. Now, if you have an asymmetrical molecule with a polar bond, like in HCl, um, there is nothing to cancel it out. There's a single dipole, nothing to cancel it, and therefore HCl, HBr, HF, they would be polar. Now, in a molecule like water, again, it is asymmetrical. And then if you look at the dipoles, hydrogen is 2.1 electronegative value, and oxygen is 3.5. All right. And so there is an electronegativity difference of 1.4. The magnitude of this dipole is 1.4, and so is this. Um, so these dipoles are heading in the same direction towards oxygen, which has the higher electronegativity value. All right. So there's nothing to cancel them. These dipoles are not canceling, and therefore water is highly polar. Again, in ammonia, you see that there are three dipoles, all right? And where are those dipoles headed or pointed towards? They're all pointed towards nitrogen, which is, I think its electronegativity value is 3, and hydrogen is 2.1. So that's a 0.9 difference. And so that, or it could be 2.8, I'm not entirely sure. But anyway, there is a electronegativity difference, and those dipoles are directed towards nitrogen. And again, there is nothing to cancel them out. So therefore, ammonia is polar, all right? So asymmetrical molecules, if they have polar bonds, they are going to be polar. All right, how do you determine polarity of the molecule? All right, first it starts with drawing the Lewis structure. All right, once you draw the Lewis structure, then determine the shape of the molecule and then see if the dipoles are canceling each other out due to that shape and the structure, or they're not. Okay, all right, so OF2. So when you look at the structure of OF2, it has this type of structure, Lewis dot structure, all right? Oxygen is the central atom, the two fluorines, the surrounding atoms, and around the central atom, you have two lone pairs and two bonds, four electron groups. However, two of them are bonds, two are lone pairs, so it has a bent shape, all right? Now, fluorine is the most electronegative element. It has a value of 4. Oxygen is 3.5. So each dipole has a magnitude of 0.5, okay? So the bonds are definitely polar covalent, okay? And again, there is nothing to cancel the dipoles, all right? They are all pointed towards fluorine, which is the more electronegative element. And again, there's nothing here to cancel them out. So again, asymmetrical molecules with polar bonds are going to be polar. All right, identify each of the following molecules as polar or non-polar, right? PBr3. PBr3 is going to have a structure very similar to ammonia, all right? A pyramidal structure. HBr is going to be like HCl, all right? A single dipole. So it's definitely going to be polar. Methane, we already know the CH bonds are nonpolar, so the molecule is nonpolar, right? PBr3, there is an electronegativity difference between the phosphorus and bromine. It's very slight though. It's 0.7, and again, those dipoles therefore will be directed towards bromine, all right? And these two might cancel, but there's nothing to cancel this out, all right? So it's an asymmetrical molecule with polar bonds, and therefore it is, the molecule is polar, all right? HBr is got a single dipole directed towards bromine, so it is polar. And CH4 has non-polar bonds, all right? So therefore the molecule is non-polar. All right. So again, determine the polarity in the following molecules. All right. Now, when the bonds are nonpolar, like in N2, then it's going to be nonpolar as a molecule. Now, if you look at CCl4, all right, in the previous slide, where was that? Did we see CCl4? All right, you see that this is CCl4. Suppose you replace this with a hydrogen, all right? Then what happens is this bond is going to be non-polar, all right? So you have two dipoles which will cancel, but nothing to cancel out this dipole, all right? So therefore, in CHCl3, which is chloroform, it's going to be polar, all right? So again, as I said, asymmetrical molecules with polar bonds are going to be polar. How about NF3? NF3 is going to look like ammonia. pyramidal structure, and though the polar bonds are directed towards fluorine, all right? Again, nothing to cancel them out. This is going to be polar. CCl4 we already saw is non-polar because the dipoles cancel. CH3OH is going to have a single dipole, all right? And that dipole is going to be directed towards the oxygen, all right? And again, nothing to cancel it out, so it's going to be polar. I2, when you have the same type of element making up the bond is nonpolar, so this is nonpolar, all right? C2F2, there is going to be bond polarity between the carbon and fluorine, all right? Now, C2F2 will have a structure. There are two carbons in the middle and two fluorines, and it's going to be kind of linear in structure. However, the two dipoles, they could probably cancel, all right? Let's look at the structure and then see what we can come up with. CO, there is only one dipole towards oxygen, so this is going to be polar, okay? Yeah, so as the two dipoles, this is a linear molecule. The two dipoles are canceling each other out, and therefore it is non-polar, okay? Right, so nitrogen, I2, when you have a diatomic molecules with similar atoms, of course, the bonds are nonpolar, it's going to be nonpolar. CCl4 is nonpolar. However, when you have a CHCl3, it becomes polar, it's asymmetrical. NF3 is polar. Again, this is polar because there's nothing to cancel out the dipole being directed towards oxygen. And then here, because there is one dipole in this direction and another dipole in the other direction, like carbon dioxide, they're going to cancel each other out. All right, we'll stop here and continue this, the next section in the next video.